Okay, so this is a continuation of yesterday's lecture on parsers, and we ended up talking about quite a few of the atomic parsers. Let me just load up the file. So you may remember we had like item, so we can apply parse, and we can apply item to a string. An item just takes back a character. And so the result of a parse is a list of pairs where the first element was the thing that was parsed. Now we had another one, primitive one, which was return. And in return, you tell it what the thing is to parse, and let's say the thing to inject as the result of parsing. And so then we get put one in there. I mean, if I say, you know, true, it puts true in there. So return is a way of returning a value. And so we had item, return, parse. Failure is a parser that just always returns the empty list. So that indicates failure, which notice is a little bit different from saying, or is quite a bit different from saying return the empty list, because then we haven't failed. We don't have the overall empty list. So we then had sat, which was let you take a predicate of characters and say like C is an element of this was the one for lowercase, and so I can say parse with this, and and it pulled off the X because it was in fact a lowercase letter, but if it had been uppercase, it would have failed. So anyway, with SAT, we were able to write a parser that could pull off a digit, pull off a lowercase letter, pull off an uppercase letter. We could specify with this char parser exactly what we want to see. We say like, okay, look, I want to see an uppercase X, and then it succeeds, and anything else will fail on this one. So we're building up this primitive library of things that lets us do various things. Now, one of the things that we did was we instantiated parsers as an instance of the monad type class. And so monads give us, the monad type class gives us an interesting way of gluing together two parsers or two things. One is a parser, and another is a function that knows how to take the return value from the previous parser and create a new parser. So, for example, if I can do, I could say like item, combine that into, and now I want to get function that takes that, whatever the character was that was eaten, and I don't know, I could say, okay, character X. And so, I don't know, I'm making this up as I go along. So if I say, Alan pulled off one X, I'm sorry, pulled off two X's. So what if I had XY? This is going to fail. So it's expecting to see two characters, and it's returning the value of the last one. Now, if I want to get them both, but I do know that they're both the same, I can use bind again to add together a new one, and I'll say that's a return of X. Oh, I gotta say lambda, and in this case, I'm ignoring it, return of X. It failed because it needs to. Okay, so then there, or I could return, say, return a pair of X's. And there, it did. So what's my point? There's a very nice, if you have, in general, if you have P1 bind, let me go up here and do this in a comment. So like in general, you have a sequence of parsers and functions composed together using bind. They can look like this. So I've got one parser, and then x1 is going to be a variable that captures what comes out of parser 1. And then parser 2, and I'll capture that with x2. And I go ... and finally parser k. And if I capture that with lambda x sub k, and then I return, and I can return some function applied to x1, x2, ... x sub k. So that parser is the same as a parser that looks like this, because we became a monad, and this bind operator is the monad composition operator. So I could say do x1 gets a value of p1, and these excuse me, these must be lined up in exactly the same column or it will not work. So x2 ... x3 gets a value of p, I'm sorry, x sub k gets a value of running parser p sub k, and finally we can return some function of x1, x2, ... up to x sub k. So this form is typically much more readable. And so the do notation, and here we use it in string. So the string parser is a parser that takes as input a string and then succeeds if you find exactly that string as the next sequence of characters in the input stream that you're looking at. So it says, look at the string. If the string is empty, then return the empty string. And, you know, we could write, like I said yesterday, we could write this like this. And otherwise, if the string is not empty, it has an X const onto some X's. And so what we do is we grab the character. We're looking for X. Remember, this parser here only succeeds if the next thing on the input string, on the input stream, is X. And then we recursively call string for the tail, and we return X. We return the string that we found, which is kind of silly. I mean, we could just make this a parser of unit that either succeeds or doesn't succeed. Maybe I should tell you what I mean by that in the, but let's just try it first. I'm going to say, I'm going to apply the string parser. It's looking for an XYZ to the string XYZZY. and I'm going to get XYZ. But if I had, like YZX or YXZ, it's going to fail because the beginning of the list is not XYZ. So this is really useful for when, when I'm looking for something like, hey, I'm looking for a plus sign in an arithmetic expression. I might have something like this. I've already grabbed the other parts. Okay, good. It succeeded. Now, what did I mean by saying like it's kind of useless to return this string? I really think because you already know what the string is that you're looking for. So you could make this a parser of unit, which just returns success like that. Now, if I reload the library, oops. What did I do wrong? Oh, this one has to return unit also. Oh, it's causing problems much later. All right. I apologize. I can call this. Let me make a copy and call it string one. And this one's going to be a parser that just says I succeeded by returning the single element of the unit type. And this is what I was saying. It will not work if everything is not lined up perfectly. So you got to keep those vertically aligned. Okay, so now if I try this, I just get back string, but if I try string one, I get back it succeeded. Now, why might you want to do that? Well, I mean, since you already know what you found, if you succeeded, then you know the next thing that was on the list was, or on the input stream was a plus. You know that you know what you got back. If it succeeds, you know that you found an XYZ. So it might make more sense to do this, but that's just sort of playing around with the return type. It doesn't really maybe help you in any significant way. Okay, so now one thing you can do is there's also a linear form of lowers of the do notation where you can write these things. Now, the nice thing maybe, and I have seen that some, more production-oriented Haskell programmers may use this style because if you accidentally do something like this, where, for example, return is not perfectly aligned, it doesn't matter because it's just looking for the next semicolon. So you can use squiggly brackets, set brackets, and semicolons to separate things. And one advantage of that is, like in the interpreter, it lets you write a do notation, in one line. With, like, if I I can say, oh, do whatever. I gets the value of semicolon. J gets the value of item, semicolon. Return. J, I, let's say, squiggly bracket, right bracket, And so that did that. That took the string X, Y, Z, Z, Y, grabbed off I, got the value of X, J got the value of Y, and then I returned them in the reverse order. Okay, so there's a whole bunch of different parsers to this one here. Remember, lower was the one that returns an individual character. And then here, lowers is recursively calling itself. So lowers will get a string of, it will get kind of like as many lowercase characters as it can. And in fact, they're all lowercase there. But then if I put, that, it will only get the first sequence of lowercase characters. If I put something that's not lowercase, like a underscore in there, it'll only read up to the underscore. So this gets lowercase characters, and then a letter is either a lowercase character or an uppercase character, and then an alphanum is either a letter or a digit. And then we have some identifiers that look like, oh, okay, grab, if you wanted an identifier like in the parsers that I build for 4780 principles of programming languages, in there we use identifiers that have to start with a lowercase letter. And then after that, they can be any numbers or letters. But, in the parser that I gave the other day, I wanted a different, for the B expressions, I wanted to be able to use capital letters. So I just changed this so that this one uses letter and then many alphanum. Okay, so what about natural numbers? Like, now see, this is an interesting thing. This is, I'm parsing with Nat. This first thing here, because the type of the parser is int, it's actually returning an int. That's an actual integer. It's not a string. It's an integer. And so how did we get it? Well, we got one or more digits. Like, you wouldn't want Nat to succeed if you had no digits, for example. That's not a natural number at the beginning of the thing, at the beginning of the input stream. So you want at least one digit and possibly many. And then you return, and read is a thing that will take a sequences of digits. And since we know the system knows that once an integer, it knows what to read it into. It reads it into an int. Now, if you wanted an int, you might allow minus signs in front of an int. So you might say like parse int, and you say like minus, whoops, I didn't mean to. And now that number over there is a minus 123. Now, sometimes you want to get rid of white space. Like, if I'm dealing with a file of numbers and I got something like this, what I can do is I can parse an int out of there, but I can also say make tokenize the int parser, which means make it read white space and get rid of white space around it. So then I can do, like this. I can get that int. Say many token int. Maybe I want to say many one. But what's that going to do? That gives me all the numbers in the list. And I didn't have to handle the white space. So what is this token thing doing? It's basically saying, okay, now what I didn't say before was, you know, if you don't have, like I don't have, you could put underscore here and say, I don't care, because white space just eats up white space. I may not care how much I got. It just is a parser of type unit. So I don't care how much I got. And in fact, in the do notation, if you don't put a variable name followed by that left pointing arrow, that means just do this parser and don't bother. The next one doesn't have, you don't pass any value on. And so here it says, eat up all the white space, then grab whatever you value you get back from using the P parser, and then eat up more white space and just return that value. And so in here, when we did the previous one, it basically said, okay, eat up the white space until you have no more white space, then parse with int, okay, and that succeeded, and then eat up white space after it. And so we got rid of the white space after, and we're starting with 133. Now, notice that white space succeeds even if there is none. It's, okay, I succeeded. There was none. So white space deletes or eats up 0 or more white space characters. And so those are spaces, new lines, tabs, and carriage returns. Now, identifier, I should probably have this. I mean, I should call this one, you know, have an identifier 1 and an identifier. But anyway, this is what I did when I reused this base code for our parser the other day. And that was, it tokenizes the identifier. So that means it deletes white space. It doesn't have to appear as the first thing as long as there's only white space in front of it. The natural token, we did that before. If I did this, that would fail because there's white space there, but NATUR, natural, is the tokenized version. Integer's the tokenized version. And then in general, if I'm looking for something like, you know, a particular string, then I can tokenize that string. Like suppose I'm looking for, and so I can say a symbol, looking for, you know, I don't know, suppose we had some funny 2-character symbol, like, or even 3, we put like a plus sign in, you know, like we're doing in Haskell, like you know, we've got some operators that look like this. And I said, you know, bunch of spaces. Now look, if I do this, that's going to fail because symbol that I'm looking for is those 3 consecutive things. And the symbol, making a symbol, says, oh, eat up white space around the thing. And that's really the primitive parsers that we write everything with. Now, I guess I should say that there are Haskell libraries, very rich parser libraries, that are better at doing handling parser errors and keeping track of where you are and helping you do that. But they're much more abstract. They're much more generalized. You can generalize what kind of stream input you're reading. You can generalize what kind of monad you're using. See, here we're using the list monad to kind of return our values, whereas we could have made it the maybe monad. And I don't know, I think if you're going to be writing actual, if you're going to be writing parsers in Haskell, you should use probably megaparsec or parsec libraries. But for us, it's just good enough to use these to just learn about parsing. Okay, so in the next lecture, I'm going to talk a little bit about how grammars can be translated into a form that will allow you to very easily, using these primitives, write a parser for that simple grammar.